So another way of working with factors is to find all the factors that two numbers share, or more importantly, find the biggest factor that two numbers share. So it's the biggest possible. So for example, if I look at the number and compare the number 6 and the number 12, I could say, what factors do they share? Well, 6 divides by 2, and 12 also divides by 2. So 2 is a common factor, right? So 2 is just a common factor between 6 and 12. 6 and 12 also happen to share the factor 3 and 3. 3 divides 6 and 3 divides 12. And so 3 is also a common factor. And that's the last of the common factors. 12 has a factor of 4, but 6 does not, so on. So if I were to take these two factors and multiply them together they equal 6. 6 would be the greatest common factor, GCF. That's how we write greatest common factor. So 6 is the greatest common factor between 6 and 12. It's the biggest number that divides 6 and divides 12. Easy enough. But when we start wanting to work with numbers bigger than 6 and 12, etc., it can get a little bit complicated. So we actually have a GCF algorithm, right? So it's the greatest common factor algorithm, ALGORITHM, algorithm. An algorithm is just a set of steps that you can follow to complete a arithmetic or algebraic goal. Algebra comes from the word algorithm. Actually, that's a little bit of a lie. Algorithm comes from the word algebra. So let's look at the algorithm for finding the greatest common factor between any two numbers. Suppose I want to compare 25 and 40. So the first thing I want to do is pop both of these numbers. So 25, the smallest prime number that 25 divides by is 5. And when I divide 25 by 5, I'm left with 5. So I've actually found the prime factorization, or the pop, for 25. Notice that 25 is 5 squared. That's the prime factorization. That makes 25 something we call a perfect square. Because it results of a prime number squared. 40, on the other hand, has more than that. The smallest number that divides 40 is 2, leaving 20. I can divide 20 by 2, leaving 10. I can divide 10 by 2, leaving 5. Now notice what I just did is I did my factor tree and hockey stick method in my head. That's why I like hockey stick method, because the more you practice it, the more you're able to do it without having to write the whole factor tree. I'm going to do the same thing again and use exactly the same words and show you that. The smallest number that divides, the smallest prime that divides 40, except for 1, because of course that would be redundant. The smallest prime that divides 40 is 2, and when I divide 40 by 2, I get 20, and I said that when I was right here. Divide 40 by 2, I get 20, which divides by 2, leaving 10, which divides by 2, leaving 5. 5 is prime, so I wrote it down. Let me do that again up here using the same language. 40 divides by 2, leaving 20, which divides by 2, leaving 10, which divides by 2, leaving 5, and 5 is prime. So notice how the hockey stick method of doing a factor tree trains your brain, your mind, your thoughts to be able to do it without the factor tree. Okay, now that I've done that, let's look for the greatest common factor. And what we're going to do is just look for factors that it shares. Well, notice I share a 5. In both numbers have a 5. I have another 5 for 25, but I don't have another 5 for 40. So the greatest common factor between 25 and 40, GCF, equals 5. It's the biggest number that divides both 25 and 40. It's the greatest common factor. Let's do a few examples to make things more clear. Let's find the GCF of 34 and 38. So the algorithm says first I want to write each as a prime, or excuse me, I want to write each as a product of primes, one over top of the other. So I have 34 and 38. Notice how I'm writing this is very specific. If you want a factor tree, just do it on a piece of scratch paper. This lesson isn't about show me that you know how to do hockey stick method. This method is about get the prime factorization. So do that on another sheet of paper or do it in your head. The biggest number that divides 34 is 2. Excuse me. The smallest prime that divides 34 is 2. When I divide 34 by 2, I'm left with 17. Notice 17 is prime. I made that up. That is so not true. Let me do that again. 34 divides by 2, which is 17. I was 100% right. I don't know why I got myself all jammed up in that. All right, 38 divides by 2. If I divide 38 by 2, I'm left with 19. 19 is prime, so I write it down. Now all I have to do is identify, and I showed you with the little loop, but I actually just like to do it with lines. 2 is the only factor, so I can say that 2 is the GCF of 34 and 38. Let's do another example. I think just a bunch of examples are going to make this as clear as possible. Let's look at 32 and 81. So the algorithm says to write one on top of the other, and then by whatever method, write each as a product of primes. So 32 divides by 2. If I divide 32 by 2, I have 16. Which divides by 2, leaving 8? Which divides by 2, leaving 4? Which divides by 2, leaving 2? And so I write the last 2 down. So 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. That's the prime factorization of 32. Let's look at the prime factorization of 81. The smallest prime I can divide 81 by is 3, which leaves 27. 27 divides by 3, leaving 9, which divides by 3, leaving 3, and 3 is prime. 3 times 3 is 9, times 3 is 27, times 3 is 81. Now I just have to draw my line through the common shared factors. Look at this, I don't have any. No common shared factors. When this happens, we say 32 and 81, meaning there's no shared factor. We call these relatively prime. So obviously 32 is not a prime number and 81 is not a prime number, but when we compare them to each other, they're prime, meaning they have no common factors. So we call it relatively prime. Two numbers that do not share a common factor at all, except for one, of course, the trivial case, are called relatively prime. Let's do another example. Let's find the GCF of 21 and 160. So again, the algorithm, right? The GCF algorithm says write them on top of each other, one on top of the other. And then by whatever method, write them as a product of primes. 21 doesn't divide by 2, it does divide by 3. 3 is the smallest prime number that divides 21. And when I divide 21 by 3, I'm left with 7, which is also prime. So I'm done. 160 divides by 2, leaving 80, which divides by 2, leaving 40, which divides by 2, leaving 20, which divides by 2, leaving 10, which divides by 2, leaving 5, and 5 is prime. And darn it, I thought I picked a number that wasn't relatively prime, but in this case, we can say that 120 and 21 and 160 are relatively prime. Because they do not share a common factor. Let me see if I can get a better example that actually has a greatest common factor, since that's the name of this lesson after all. How about 18 and 24? So the algorithm says, write them on top of each other, and then write them as a product of primes, each in turn. 18 divides by 2, leaving 9, which divides by 3, leaving 3, and 3 is prime. 2 times 3 is 6, and 6 times 3 is 18, so I know that's correct. 24 divides by 2, leaving 12, which divides by 2, leaving 6, which divides by 2, leaving 3, and 3 is prime. Let me double check that. 2 times 2 is 4, times 2 is 8, and 8 times 3 is 24. So I know I have the right product of primes, and now I want to find shared factors. They share a 2, and they share a 3. So the GCF, the greatest common factor of 18 and 24, is 2 times 3, which equals 6. Cool. Now, we can also find the GCF of monomials. So what about monomials? Well, you know that a monomial is a number that has a sign and a numeral and a variable configuration. So let's look at 6x, see if we can find a greatest common factor for 6x and 15x. First thing, use the algorithm. Algorithms are only great if they always work. Sometimes we use algorithms that only work in specific cases, but the best ones work everywhere, and this is one that does. I'm going to write 16x as a product of primes. The 16, start with just the numeral. 16 divides by 2, leaving 8, which divides by 2, leaving 4, which divides by 2, leaving 2, and 2 is prime. And then I have 1x multiplied in as well. So 2 times 2 is 4, times 2 is 8, times 2 is 16, times x is 16x. Let's do the same thing for 15. 15 divides by 3, leaving 5. 5 is prime, and then I have an x. So 3 times 5 is 15, times x, 15x. Now let's find all the factors that are in common. Well, I have a bunch of 2's in 16 and a 3 and 5 and 15, so I have no integer factors that are in common, but the x is shared. So the GCF for 16x and 15x is only x. That's the biggest number I can divide both numbers by. That's the biggest factor I can divide both numbers by. Let's do another example. Let's do 32y squared and 6x squared y. Okay, this is our last example, and it looks like we're going to go out with a bang. 32y squared and 6x squared y. Product of primes for 32. 32 divides by 2, leaving 16, which divides by 2, leaving 8, which divides by 2, leaving 4, which divides by 2, leaving 2, and 2 is prime, so I'm going to write it down. And then I have a y squared. Oh, I'm running out of room. Let me move this over. You got to love this electric paper, right? 2 y's. So that would be y times y. For 6, 6 divides by 2, leaving 3, and 3 is prime, so I'm going to write it down. X squared means I have an x and an x, and then y means I have a y. So now let's find the GCF, which means I have common factors. So I have 2 2's. I have a 1 2 in each, I should say. So that's a common factor. A bunch of 2's here, a 3 here. I'm done there. I have x's in the 6x squared, but I have no x's in the 32y squared. But I do have a y in both of them. So I'm going to write that down. And that's everything that's common. So the greatest common factor, 2 is a common factor, y is a common factor. But the greatest, the biggest common factor is 2y. So that is the algorithm and the explanation for greatest common factor. We're going to use these in so many ways in algebra that this is one of those processes. Not that every algebraic thing I show you isn't important, but some of them are more important. And this is one of those more important things. There's a great algorithm to work with to find the greatest common factor, put a G there, and it works with integers, and it works with monomials to find both integer factors and variable factors. In this case, the integer factor would be, we don't write it, but there's a 1 out front, and the variable factor is x.